derivative, you get lost in the quotient or the product rule for the moment, but then kind of reorienting yourself and figuring out what you're supposed to be doing with the derivative. So simple stuff, writing the equation of a line tangent to the function at a given point. We've done a lot of this with basic derivatives, but now, like I said, we're going to get lost in a quotient rule on this particular one, and then we're going to have to come back out of it. So writing the equation of a tangent line, you need a point. We have it. And you need a slope at that point. So the slope at 0, so we need f prime at 0. Well, before we can do that, we have to find f prime. So it's just going to be a detour to find the derivative. So go ahead and do that. There's really not much simplifying to be done here. And then here's another thing that I didn't really come up when we just went over the homework, but it's going to come up. If your end goal is to evaluate the derivative at a specific point, you don't need to waste time simplifying the derivative down to perfection, okay? If the directions are to find the derivative and simplify, then yes, of course. But if the directions are to evaluate the derivative or find the slope at 0, you don't need to waste time doing all that. You can just immediately plug in. So, and sometimes you might choose to simplify just for your own betterment on finding the value of the derivative at a certain value, but you don't have to if you're feeling lost. So that's going to be 4. E to the 0 is 1. Minus e to the 0 is 1 over 0 plus 4, 4 squared is 16. So that's just 3/16. There's where we were in the larger, grander scheme of things. So we're going to write this equation. So y minus a quarter equals m x minus 0. So that's just going to be y equals 3/16 x plus a fourth. Now, for fun, because I like to do this, literally for no other reason, e to the x divided by x plus 4 is our equation of the function, and 3/16 x plus a quarter. Oh, man. There's my e to the x function. There's my tangent line supposedly at 0 1/4. So if I zoom in to the origin, I should see that a little bit nicer. Here's my tangent line. If you want a second trace and find the intersection, that should put you at the point of tangency. 0 1/4. Wonderful. Any questions? So, review. We've done that concept before. Determine the points at which the graph of the function has a horizontal tangent line. What do you know about horizontal tangent lines? Slope f prime of x has to equal 0. Correct. So we're going to find the derivative and set it equal to 0. Now this is giving us an interval along which we're looking for this. So that tells me, and that makes sense, because it's a trig graph. There's probably a gazillion places where it has a horizontal line, because if it's got 1 and this thing is cyclical because it's trig, it's going to have a gazillion. So specifically they want us only looking for the location and the points that are between and along the interval of an x of 0 and an x of pi. So when we find the derivative, that may play a role as we move forward here. We need the power rule. Or not power. product. I wish those two words weren't so close to each other, meaning they both start with a P. Product rule. First times derivative of the second plus the second times derivative of the first. So if I want to simplify this, really what can I do? Factor out the e to the x. And that is helpful because I'm looking for where this derivative equals 0. So essentially when I set it equal to 0, the fact that I factored it out now allows me to use my zero product property, teeing it up, right? So either e to the x equals 0, which happens never, or the cosine of x plus the sine of x equals 0. Only on the interval from 0 to pi. So I'm going to think about my unit circle for a second. So 0 to pi. If those two need to equal 0 when you add them together, they need to be opposites of each other, yes? One has to be positive, one has to be negative. Do we follow? Or they could both be 0, but I think we should know that that never happens. As individuals, you won't have 0 plus 0. So which quadrant does that eliminate? First, because everything's positive there, and a positive plus a positive will never equal 0. So where would we be in the second quadrant where the cosine and the sine have opposite values? Liam? 3 pi over 4. Okay? Cosine of 3 pi over 4 is negative, radical 2 over 2. And the sine of 3 pi over 4 is positive, radical 2 over 2. So x equals 3 pi over 4. That's, unfortunately, work I can't really document. You have to think through that, as is typical with trig. So that's the only x coordinate that will happen at? Yes, right? On that interval, correct. So if I know that that's my x coordinate and I'm just looking for the point, where do I go to find the y coordinate? Plug it in where? Well, I see an x in a gazillion places. Are you really going to put it all in all those places? The original function, correct. So I'm going to do e to the 3 pi over 4 times the sine of 3 pi over 4. Not going to be pretty. It's just going to be e to the 3 pi over 4. Can't do much with that. Times root 2 over 2. So that's the ugly y coordinate that I have to live with. I'm going to write it as root 2 e to the 3 pi over 4 over 2. Again, for fun. Let's take a peek at this function. Oops. E to the x, sine x, mode, radians, window. I'm going to do negative 2 pi to 2 pi just to see the cyclical graph. I don't know what window's appropriate. That's going to take some playing. Ooh. So you can see the horizontal tangent line. If I do second trace and look for that maximum point, left bound, right bound, 2.35, which I'm guessing is 3 pi over 4, and 7.46, which is obviously that. Yes? Any questions? Okay. This next one is more of like a kind of white, trying to shed some light on something. So we have two functions, an f of x function and a g of x function, and they want us to verify that the derivatives of them are going to be equal. So if we use our quotient rule on this one and quotient rule on both of them would be appropriate. So your bottom times the derivative of your top, cosine x minus 3, minus your top times the derivative of your bottom is just 1, all over bottom squared. We get x cosine x minus 3x minus sine x plus 3x all over x squared. And your 3x's cancel, minus 3x plus 3x. So there's our first derivative. Second one, quotient rule, bottom times the derivative of the top minus the top times the derivative of the bottom, which is just 1, all over bottom squared. It's going to simplify x cosine x plus 2x minus sine x minus 2x. Your 2x's are going to cancel, and we get the same thing. So we verified. Then explain the relationship. Why would their derivatives have been the same? When have we seen two functions whose derivatives are the same? They're parallel. Yes, so one's like a shift of the other is when we've seen that. So how could we explain why one of these is a shift of the other one? If you split them up, yeah, go ahead, Liam. Yeah, go ahead. Everyone see that? They look obviously totally different because that's all hidden in the fact that they got a common denominator and condensed them into a single fraction. So you don't see it as clearly, but if you split it up, you can see that. One's just shifted up 5 units. Good? Okay. Uh-oh. Oh, no. I didn't realize this. Or did I? Oh, yeah, I did. Okay, so obviously I didn't want to copy down something crazy, so I'm going to open this up to do page 155, number 88. Oh, because it's a picture. Okay, so use the graphs of f and g. Let p of x be the product of the two functions, and q of x be the quotient of the two functions. So in A, they want us to evaluate the derivative of p at 4. So let's see. P of x equals f of x and times g of x. I didn't need that sentence. F of x times g of x. So if they want us to find the derivative of p, that's going to require what rule? Product first times the derivative of the second. Keep putting that parenthesis in because I'm used to it. Derivative of g is g prime of x. Plus the second times the derivative of the first. Now specifically at 4, p prime of 4 is going to be f of 4 times g prime of 4 plus g of 4 times f prime of 4. And then we're going to look at our charts to see why and how we're supposed to know all of that. So our graphs are giving us f and g. So what is, first things first, f of 4? One. Here's our f function. F of 4 is 1. What is g prime of 4? So here's g, this lighter function. What is the slope at 4? 0. plus g of 4, so we can just look right at the g graph. What is g of 4? 8. And f prime of 4. What is our slope at 4? Now that's on a linear portion, so whatever the slope of that section is going to be the slope at 4. So that's a rise 1, 2, run 1, 2, 3, 4. Rise 2, run 4 is a slope of 1/2. So that's 0 plus 4 is 4. That was fun. No? And 90. Oh no, we have to do q prime of 7. Okay. Q of x. They have defined as f of x over g of x. So for q prime of x, we're going to follow our quotient rule. So our bottom times the derivative of the top minus the top times the derivative of the bottom all over bottom squared. So specifically q prime of 7, g of 7, f prime of 7 minus f of 7, g prime of 7 over g of 7 squared. Are we ready? It's a big maze. What is g of 7? 4 times the derivative of f at 7. So again, at 7, the f function is linear, so we just got to look at the slope of that. Rise 1, 2, 3, 4, 5, 6, 7, 8 over 1, 2, 3, 4. What's that a slope of? 2. Minus f of 7 is also 4. The derivative of g at 7 is on a linear stretch, so down 1, 2, 3, 4 over 1, 2, 3, 4. What would that slope be? -1 over g of 7, which we already figured out was 4 squared, so that would be over 16. So we have 8 plus 4 is 12 over 16 is 3/4. Any questions? All fun stuff. Number 90. The radius of a right circular cylinder is given by root t plus 2. What do my good little math students do right now? No. Before that. I haven't even read the rest of the question. Draw a picture. I don't know if you need it, but it's always helpful to have your mind in the right place. So the radius of that is root t plus 2. Especially when you're dealing with a type of question that looks unfamiliar to you and you don't really, you haven't seen a bunch like this. And its height is 1/2 root t. Where t is time in seconds and the dimensions are in inches. Find the rate of change of the volume with respect to time. So the volume formula is pi r is root t plus 2 squared times your h of 1/2 root t. So we want to derive this. Find the rate of change of volume with respect. Rate of change is derivative, yes? So how do we want to handle this? we can simplify this out. So just rewriting the original. So the square root of t plus 2 squared is just t plus 2. Yes. Why don't we need the absolute value there? Remember that feature? Well, it's really because this has to be positive anyway, right? It's this whole thing has to be positive anyway. It's your radius. So that will just be pi times t plus 2 times a half root t. So even still, that'll be pi over 2. I'm going to put my root t first, times t plus 2. Would you like to do the product rule, or would you like to distribute? You want the pi over 2 inside? You can. So you want the pi in here. So pi t plus 2 pi. And let's just keep the root t over 2. Like that. That's fine. And you want to do the product. Or do you want to distribute? Lots of options. Doesn't really matter. Okay, product. So v prime. Oh, man. Can I rewrite this? T to the 1/2 over 2. So our first, I don't like this. I'm going to keep it like 1/2. First times the derivative of the second, which is just pi, plus your second times your derivative of your first. So your 1/2 out in front where there's already a 1/2 is going to be 1/4 t to the negative 1/2 power. So that's root t pi over 2. Plus pi t plus 2 pi over 4 root t. I have a sneaking suspicion that the back of the book would get a common denominator. Is anyone bursting with excitement to do that? We don't have to. Okay. Any questions? Okay. So there's your homework. And what do we got here for time? 5 minutes? I will throw it up.